So good afternoon to all. Today we are going to learn a topic about tolerance. On behalf of AICTE PRERANA scheme for preparing GATE examination for SCST students for the higher education purpose. Myself D. Harihara Shayee, Assistant Professor, Department of Mechanical Engineering, Erode Sengunthar Engineering College. So today's topic is about tolerance, right? So first we want to know about what is meant by tolerance. Tolerance is an it may tolerance also manufacturing tolerance or engineering tolerance, which is permissible limit or limit of variation in a physical dimension, which a measured value or a physical property of a material, manufacturing object, system, or services, or other measured values such as temperature, humidity, physical dimensions of any component may have a tolerance, which they want to satisfy the conditions also. Likewise, dimensions, properties, or any conditions, it may be thermal, physical, or mechanical. There are many various certain things which need to meet the practical limits without significantly affecting their functional of the equipment and processes. The tolerance are specified to allow a reasonable leeway for imperfections and inherent variability without focusing on the interchangeability, tolerancing its standards, tolerance and its types, general definitions, hinge tolerance, metric tolerance, sorting tolerance, tolerance accumulation, and formatting tolerance methods. So, first, what is meant by tolerance? Already, I have given the definition. The tolerance is a total amount a specific dimension is preferred to vary. Right? A second one definition, limits. The limits are the maximum and minimum size that the parts is allowed to be manufactured and to be assembled. What is meant by basic size? The basic size is the size from which the limits are calculated. Like us, from the basic size only we can calculate the tolerance and limits and all. Here a first topic, tolerancing for interchangeability. The tolerancing is dimensioning for interchangeability. Here what is meant by interchangeability? An interchangeability part is simply a mass-produced part, a replacement part, or matting or assembled parts, which would make a proper assembly without compromising the working performance. Here we can know that how is a future on an interchangeable part dimensioned. The future is not dimensioned using a single value but a range of value, right? Which one is a basic size here. From the basic size only the tolerance value has been mentioned here, which one is on basic size and plus 0.005 and minus 0.006 is a tolerance value. Already we know that the tolerance is the amount of size variation permitted, right? You can also choose your tolerance that specifies a large and small variations, which means a small limits which starts from 0.0042 and end with maximum limits 1.005. Here the total amount of tolerance is 0.11, right? Which the 1.005 and 0.994 is a tolerance limit, which is meant by a minimum and maximum limit, which is calculated from the basic limit value, right? Which is the basic limit value? Yeah, 1. Here, why do we want a part size to be controlled by two limits? Here we can ask a question that why it cannot be a one value, right? So I think we can't able to make or manufacture or fabricate any component with an accurate value, right? So there is always a limit which it carries upper and lower value. So already we the term itself mentioned that there it needs a two values. One is upper and another one is a lower value. So always we need a two value limits. That's it is necessary because it is an impossible to manufacture two parts without some variation. The stator limits are a form of a quality control. Already they have a chart which is called as a tolerance limit chart, and the chart carries a minimum and maximum tolerance value from its basic limit value. So between that upper and lower limits, we can manufacture a component. Choosing a tolerance for your design. So when we consider such things, we want to need some of conservation, like a specific tolerance with whatever degrees of accuracy that is required for the design to work properly. And here choosing a tolerance that is not unnecessarily accurate and excessively inaccurate. So what are the factors that we want to consider to choose a tolerance value, right? Here some of the values, sorry, some of the points are given. Choosing the correct tolerance for a particular application depend upon the design intent, end use of the part, which means the end use of the part means the working condition, right? And the working life of a component, right? And also which type of fitting or matting or assembly are needed. And second one is the cost. The most important factor which falls on the final component is a tolerance, right? If you need more accurate tolerance means the cost of the manufacturing will also leads to increase. And third one, how it is manufactured. How it is manufactured means the way of using the equipment. By either use the conventional traditional method or by NC machines or by CNC machines or by DNC machine. It's depend upon the way of manufacturing. The component manufacturing cost of the components also vary. And also at the same time the finished quality of the component and the accuracy tolerance also will vary. And fourth point is the experience, right? The experience means the labor. Based on the labor experience, the final component and its dimension, physical dimension, and will also vary. Next one is tolerance in standards. Standards are need to first point make it possible to manufacture parts at different times and in different places that still assembly properly. And second one, establish dimensional limits for parts that are to be interchangeable. There are two common standards available, which the two things are used to mention the tolerance value in unique manner throughout the world. First one is called as American National Standard Institute, ANSI or ASME, and second one is International Standard Organization. In India, we are following the ISO method, International Standard Organization method. So, what are the tolerance types? So, tolerance types. Here, basically, tolerance are commonly divided into three methods. And first one is limit dimension, second one is plus or minus tolerance, and third one is page or block tolerance. In first one, in limit dimensions, the limits are the maximum and minimum size that a part can obtain and still pass inspection. Here, which shown here, the symbol notifies that it is a diameter of a shaft or diameter of a hole, right? Here they give an example, right? The diameter of the shaft may be specified as follow. With a which is symbol is notified for a diameter with carrying 1.001 with lower limit 0.999. Either it may be the upper limit, lower limit may return in upper and lower, or else it can be mentioned in horizontal manner also with continue to the symbol of diameter. That's where here they have mentioned the high limit is placed above the low limit. When both limits are placed on one line, the lower limit precedes the next high limit. So second method is plus or minus tolerance. In this plus or minus tolerance gives a basic size and the variation that occur around the basic size. Here the basic size is 10 with carrying the maximum tolerance of plus 0.1 and with a minimum tolerance of minus 0.2, which it gives the maximum of a component size is 10.1 mm with a minimum value of 9.8 mm. And third one is page of block tolerance method. Here, the page tolerance is actually a general note that applies to all dimensions not covered by some other tolerance method, which is means they have given symbol alphabet number like x, double x, triple x, and 4x and 5x and all, which that each x carries some amount of values, which are tolerance values with a plus or minus value, right? For each of this component, they have mentioned the tolerance by these notations only. So next topic, shaft hole assembly method. Here, in shaft hole assembly method, from the diagram, we want to identify some of these things. Like here, both the shaft and the holes are allowed to vary between a maximum and minimum diameter, which means a shaft also carrying a two limits, upper limit, lower limit, and a hole also. Here, this component with a solid component with carrying a hole also having an upper limit and a lower limit, right? So based on this fitting, there are three types of limitations also available, right? Which is also known as a unilateral, bilateral, right? And next here, inch tolerance definitions. Here is an example for it. From the above diagram, we want to calculate the what is the limit, basic size and tolerance of the shaft and hole. Here, the shaft is maximum size is tolerance value is 0.51 and minimum is 0.47, right? As the same as a hole dia is 0.50 and 0.49. So there are the limitation given upper limit and lower limit for a shaft and a hole. So the limit we want to take and write in this table and a basic size which are 5 or 1 by 4, 1 by 2. And from that we want to calculate the tolerance, which is mean by 0.51 minus 0.47, which gives zero point 0.4, and for a shaft and for a hole 0.50 minus 0.49, which gives 0.1 as a tolerance values. Here is a inch tolerance definition. A maximum material condition MMC. The MMC is the size of a part when used in a least material condition. The LMC is the size of a part which it consists of a least material. So based on the upper limit and lower limit for the shaft and same for a hole, it may vary by selection of the which of the limit, whether it may be upper limit or a lower limit. Based on the any one selection, the final component will come under as MMC or a LMC. So, so this is an example of a MMC and LMC, right? a shaft has 0.51 and for hole 0.49, and for a LMC a shaft has 0.47 and a hole have 0.50. So maximum material condition and least material condition. A shaft with having dia. If example, if the shaft having a basic dia of 5.51 maximum and a minimum of 5.47 means the maximum material condition which takes place on the 5.51, right? And for the least material conduction which the shaft carries means for 5.47 dia rod, as well as same for hole. It may interchange, right? Simply we can say that it is an opposite to the shaft method. For a hole, with the hole having minimum amount of dia will carry the maximum amount of material, and the maximum amount of hole size carry a less amount of material. There is a tolerance definitions, maximum clearance and minimum clearance, right? So first one, the maximum clearance, the maximum amount of space that can exist between the hole and the shaft, right? So maximum clearance LMC hole minus LMC shaft condition. And second one, minimum clearance allowance, the minimum amount of space that can exist between the hole and the shaft. So minimum clearance is MMC hole minus MMC shaft. Maximum material condition of hole minus maximum material condition of shaft. So here the calculation made for maximum clearance and a minimum clearance. For maximum clearance, the formula is LMC hole minus LMC shaft. So here for LMC hole is 0.50, for shaft 0.47. So we want to minus the both values. So 0.50 minus 0.47 equal to 0.3. As well as for minimum clearance, MMC hole minus MMC shaft. For MMC hole means 0.49 minus MMC for shaft means 0.51, which it gives minus 0.2 value. Here, second, we want to know that what does a native clearance mean, which the clearance value comes with a native sign. It's an native clearance mean value, right? So, from the above slide, we can note that the minimum clearance have came with minus value, which here mentioned as a native clearance mean value. Next, types of fits. There are four major types of fits available in industries, and nowadays they are using the above mentioned here only. One is clearance fit, another one is interference fit, and next one is transition fit, and next one is line fit. So what is meant by clearance fit? There is a always space between a shaft. For example, I have mentioned here, mentioned as an example of a shaft and a pipe, hollow plate, right? If you are matting to parts like a shaft and hole means there is always a clearance between those components, two components, which means the minimum clearance value is greater than the zero value, right? Which is called as clearance fit. We can easily assemble a component of a rod and the hole easy manner without any external force or pressure. And second one is interference fit. There is never a space. There is no clearance or no limits between two matting parts or two assembling components. The maximum clearance value is always lesser than or equal to zero. So we need some of external force to assemble those two components. And third one is transition fit. Depending upon the size of the shaft and hole, there could be a space or no space, which means the maximum clearance always greater than zero and a minimum clearance always less than zero. Little bit it is near to the interference fit. And fourth one is a line fit, which there is a space or a contact. Hole dia equal to shaft dia. Example, the maximum clearance is always greater than 0 and minimum clearance equal to 0, not less than or equal to. A minimum clearance always equal to 0. This is called as a line fit. So here are some of exercise for types of fits and examples. For everyday life, we have using some of things which comes under this type of fits also. Here are some of examples of clearance and interference fits. First one, clearance fit and its examples. Lock and key. So every day we can lock and unlock our door, or we may use a key in our bike or car. We can see that there is some of clearance between the key and the keyhole. We can easily insert the key into the key point, right? So it is a simple example of a clearance fit. And also a door and door frame and coin slot. Example for coin box, right? We can easily put a coin into the coin slot, right? So we don't do not any external force to send the coin inside. There will lot of clearance available between coin and the slot. And second one is interference fit. That pin in a bicycle chain. So we can see that there is very less amount of gap. We can find that in the bicycle chain and a pin. Hinge pin, hood pick, and a hammer ties are a simple example for an interference fit. So next here we're going to know about the topic of metric tolerance definitions, upper deviation. Right? The upper deviation is the difference between the basic size and the permitted maximum size of a part, which means the maximum upper limit to the basic size. So we can simply give a notation as UD equal to basic size minus capital D maximum, right? Same as another definition is a lower deviation, right? The lower deviation is the difference between the basic size and the minimum permitted size of a part, right? So for a lower deviation, we give notation as capital LD equal to basic size minus capital D sufficient minimum permitted size value. Another one, the fundamental deviation. The fundamental deviation is the closest deviation to the basic size. The fundamental deviation is the smaller of the UD and the LD, upper deviation and the lower deviation, right? The fundamental deviation is lesser than the UD and the LD, right? And here, letter in the fit specification represents the fundamental deviation. Likewise, we have mentioned UD and LD. There is a simple example for UD, LD, and FD. For upper deviation, first we can take a shaft. For the upper deviation is if we consider as 2 mm dia of a shaft means the upper deviation is 0.2, which means 2.2 mm, and the lower deviation is 2.1 mm, which comes to 1 mm, sorry, 0.1 mm, right? So the fixed deviation is 0.1 mm. As well as for hole, it starts with 2.0. The hole is an exact size of 2.0, the basic size, and the upper deviation same 0, and the lower deviation is 1.8, which means minus 0.2, and a fixed deviation again which falls on a basic size only, so 0. Here is an exercise to find the type of fit, which the shaft of basic size 2 mm with upper deviation 2 or 0.2 and lower deviation 0.1, and for the shaft, sorry, hole, basic size of 2.0 dia with upper deviation same 2.0 and lower deviation 1.8, which it falls on an interference fit. We need some of external force to send the shaft inside the hole. because the size of the shaft is little bit larger than the size of the hole. And next one, metric tolerance definitions. Here in this MTD, International Tolerance Grade Numbering Method, which shortly known as IT, right? The ITs are a set of tolerances that vary according to the basic size and provide the same relative level of accuracy within a given grade. So the number in the fixed specification represents the international tolerance value, and a smaller number provides the smaller tolerance value. And second one, tolerance zone. Here the fundamental deviation in combination with the international tolerance defines the tolerance zone. The IT establishes the magnitude of the tolerance zone or the amount that the dimension can vary. The fundamental deviation establishes the position of the tolerance zone with respect to the basic size. A metric fit is specified by stating the fundamental deviation and the international tolerance value. Right, the amount that the dimension can vary, tolerance zone size, and the fundamental deviation letter, which is to establish the position of the tolerance zone with respect to the basic size. A hole with uppercase and a shaft with a lowercase, which notations are used to specify the values. The fits are specified by the using letters. Fundamental deviation as a letter and IT international tolerance grade for a grade hash system. When specifying it, the hole comes under uppercase letter and the shaft comes under lowercase letter. So for example, metric fit, which the H. H means the hole comes with capital letter H11 plus the C comes with a lowercase letter, which indicates the shaft with number of 11. So here metric fit designation. A simple example given for the appropriate name for the fit component, right? So a symbol, sorry, a symbol of diameter which carries a 50 mm, which is a basic size, and next to that proceeding capital H, which indicates the hole tolerance value, which next 8 it comes IT international tolerance value, and next to that a small f shaft tolerance zone, and next to the small f the value of sound comes the international tolerance value. So this is an fundamental deviation and its notations for a fit component. Yeah. Another ways are used to define the what type of system we are using, which is a basic hole or a basic shaft method. Metric limits and fits are divided into two systems, which first one is an basic hole system, another one is a basic shaft shift system. In the basic hole system, it is used when you want to basic size to be attached to the hole dimension. For example, if you want to tolerance a shaft based on a hole produced by a standard drill, reamer, or bouching any other processor, right? For example, if you have bought a component with an hole and you need to attach some of shaft with that, means you want to give a tolerance to the shaft, right? Which means you want to give a tolerance based on the which the component having a hole which you have bought from the another place, right? Based on the hole only, we can able to define the tolerance value on the shaft. This is the first method, which the tolerance is made based on the hole. And second one, a basic shaft system, which it is used when you want to basic size to be attached to the shaft dimensioning. For example, if you want to tolerance a hole based on the size of a purchased standard drill rod. If you have purchased a rod or a shaft and you need to make a hole, means the tolerance which we have given for the hole is based on the dimension of the shaft, right? So which is either the both basic hole and basic shaft are mirroring method. Sorry, mirror, it's not a mirror method. It is an opposite method. And next one is systems. Here, identify the types of fit and the system used to determine the limits of the following shaft and hole pairs. Here I have given some of the values for the shaft and holes, and we need to define which type of fits it under comes and which type of system it under comes. Which a shaft having 9.972 to 9.987 mm and with a hole of 10 mm to 10.022 mm, which it comes under clear fit, right? Because there are a little bit amount of gap available in the shaft and the hole. We need not need any external force to assembly the shaft inside the hole, so it comes under clearance, and based on the hole only the shaft is manufactured, so this come under hole system. And second one, a shaft having dia of 60.002 mm to 60.021 mm and a hole having 60 mm to 60.030 mm. Here you can see that the clearance between the shaft and the hole is little bit less when compared to the previous one. So some of we need a extra force to make an assemble or to fit the shaft inside the hole. So it comes under transition. Again, based on the hole dia only, the shaft has been manufactured. So it comes under hole system. And third one, a shaft having dia of 39.984 mm to 40 mm and hole having dia of 39.924 mm to 39.949 mm. So here can we clearly see that the shaft dia is a little bit larger than the hole. So we need it is a interference feed. We need a little bit of extra amount of energy to make an assembly, and here the hole is manufactured based on the shaft dia value. So it's come under shaft based system. So next one, metric limits and fixed. So previously, I have mentioned you that there is an instance of standards available for a tolerance. Just they given by a number, mentioning a number like N30, capital F7 slash C11 or P11 or whatever it may be, right? So each number that carries an sum of values uniquely throughout the entire world, right? So from the above system only, throughout the world, they have given a tolerance to a particular component based on the manufacturing method, material, working condition and all, right? So here we are going to find a tolerance value for an system having N30 capital H11 slash small c11, right? So this is a table example, right? So which having a capital H which defines the whole value and small alphabet which defines the shaft value, right? So here capital H11, small c11, which comes under N30. So from this table basic size, N is basic size, so N30. So in the basic size we want to take a 30 value and just mark it. And next we want to find note that the H value and C value. So capital H11, C, small c 11. So which comes whole H double one and shaft C double one. And we also got to mark it. So it is found that the basic size of 30 mm having maximum value for hole 30.130 with minimum of 30 mm and for shaft 29.890 mm and with minimum value of 29.760. So this is an international standard available throughout the world to make an tolerance unique to manufacture. So if the tolerance value differ from one place to another place means we cannot make an assembly properly. So we cannot use the component or it may be affect the working efficiency. So here is an exercise. Find the limit, tolerance and types of it and types of system for an N30 H11 bar 11 fit. So already we have taken the values from here. Minimum and maximum value of shaft and a hole. For shaft 29.760 to 29.890, right? So that have mentioned here. And for a hole 30 to 30.130. So that also mentioned here. So tolerance used by nothing but a maximum value minus a minimum value. So from that we have calculated the 0.13 for shaft and for 0.13 for an hole. So this system comes under, which means the same both having a equal value, so comes under hole, and which it comes in clearance but loose running set. So next one, same as an exercise for another one system, which having a value of N30, capital P7 slash small h6. So you want to find out the limit, tolerance and type of fit and which comes under which system. So which the N means basic size of 30, which capital P, yeah, hole size and its small h, yeah, shaft size. So again the basic size of 30 maximum minimum with having a locational interference, right? Hole P7, capital P7, a shaft h6. So which the hole having a maximum and minimum size 29.986 with minimum of 29.965. For a shaft, the maximum size of 30 and a minimum size of 29.987. So again, we have noted the two values and tabulated here for a shaft and a hole, and we want to calculate the tolerance value from the maximum limit minus smaller limit. Here for shaft it comes 0.013 and for a hole 0.021. So here based on the shaft only the whole have been fabricated, so it comes under shaft, and then it comes already a table has been noted that it is an locational interference. So we need some of external load to insert a shaft. The next one is selecting tolerance. Here, the tolerance will govern the method of manufacturing. When the tolerance are reduced, the cost of manufacturing rises very rapidly. So which reduce tolerance are which have been reduced means increase the accuracy level of the tolerance or increase the accuracy level of the manufacturing, which leads to rapidly increase of the cost of manufacturing, right? So yeah, specify a generous tolerance as possible without interfering the function of a part. So based on the working condition only, the tolerance value has been decided because it's directly affect the cost of the final component. Here some of the factors are listed: length of the engagement, bearing load, speed, lubrication, temperature, humidity, and yeah, material used. So above considering the above points, the tolerance value has also been given. If example for a bearing means a bearing which works under a fatigue load, right? So it's nearly a little bit of high accuracy tolerance, right? Which it leads to a increase in cost also. If some other components which has been used for very low purpose means we cannot give the more accurate value of the tolerance. Little bit is enough. And also previously we have said that the experience plays an important role to manufacturing a component. So all these factors will affect while assembling the component. So here, dimensioning and its grade are given here tabulated from mapping form. You may check it and note it. Right. You may go to next slide. So next one is tolerance accumulation. Right. Accumulation is with the total value. Right. Yeah. The tolerance accumulation. The tolerance between two features of a part depend on the number of controlling dimension. Here we can see a stepped bar, right? Each step carries an individual tolerance value, right? And finally, this individual tolerance will want to add it together, and finally we can accumulate as an tolerance accumulation. So either the accumulation value may be mentioned as a single dimension or a multiple dimension. You have seen shown here, right? For each step, we can also give an individual value, tolerance value, or we can give an accumulated value, right? With a single notation. So we can calculate here, right? The maximum variation between two features is equal to the sum of the tolerance based on the control dimension. So we can calculate from A to B, right? A face of A to a face of B means 20 plus 30 plus 20, which comes 70 mm with a accumulated value means plus or minus 1, right? While adding into the segments, it gives plus or minus 3. So remember, if the dimension does not have a stated tolerance, it has an impulse tolerance value. So here is an example. So here we are going to see an exercise. What is the tolerance accumulation for the distance between surface A and B for the following three-dimensional method? So here the surface phase between A to the B, which already we have calculated that comes 20 plus 30 plus 20 equal to 70 with accumulated tolerance value plus or minus 1 plus sorry, zero point 0.1 plus 0.1 plus 0.1, which comes plus or minus 0.3. So from that we can manufacture two way of a component. One is perfect component, right, with a 70 mm of a component, and another one is the maximum Wurzel size. Maximum Wurzel size is maximum limit size, right? Maximum limit case, which 70.3 mm, and another one is minimum worst case, minimum limit value, which comes 69.7. From the basic size, we have minus that zero point 0.3 value. Here is another one exercise. If the accuracy of the distance between surface A and B is important, which dimension method should be used? So this is for your own exercise. Can you note it? And you want to make the maximum and minimum worst cases. So next one is over dimensioning. Video, NPTEL. So assuming that the diameter are correct, explain why the object is dimensionally incorrect. Right? Here the diameter are given as correctly, on which dimension, physical dimension given, the given diagram is incorrect. You want to find it. If anyone have an idea, kindly tell me. Or else we can see next slide. Yeah. So here is some of mistaken things are noted here, right? First one is the decimal places does not match, right? For which the basic size having 2.00 and the given tolerance value is only in the decimal value of zero point 0.2 digit, either plus 0.1 minus 0.2. Sorry, I have wrongly informed you, but plus 0.01 minus 0.02. So here we want to ensure that the decimal values should be remaining the same count. Okay, given first mistake here, and second one is the dimensions are inconsistent. Which they have mentioned inconsistent means we want to note it clearly. The first one is the length of the component, right? A body and a pin. For a body, here the maximum deviation and the minimum deviation have been calculated, which comes 2.97 and 3.01. And for the entire body and the pin, it comes around 2.98 to 3.0, right? So which means the dimensions are overrated, right? So next one, formatting tolerances. So formatting metering tolerance is another topic. So tolerance forms standardized fit tables are listed on drawing as here some of the standards are available to mention how the tolerance has been noted, right? So here again the diameter symbol used with diameter of 20 point, maximum limit 240 with a minimum limit of 20.110. So it has been mentioned as in bracket a dia of 20 C11, which the C11 has been noted from the table, right? Previously we have found two tables, right? So from that we want to take on it. In diagram, in engineering graphics diagram, they have only mentioned that dia 20 C11. So from that we want to take out the value from the Mr. Tolerance table. The person reading the print has to have access to the standard fit tables, right? They don't mention like this, right? Dia of 20.240 upper limit and lower limit of 20.110 and all. They have just mentioned dia 20 C11. So the person who reading the diagram should take the table tolerance table and they want to note it and fabricate the component. The next one is unilateral tolerance method. So in this method, any one of upper limit or a lower limit should be as a 0 as a value and another one as another one have either plus or minus value. So a single 0 without a plus or minus sign should be present there. So basic size of 40 with tolerance upper tolerance 0 and lower tolerance minus 0.02 or either basic size of 40 with upper tolerance plus 0.02 with a lower limit of 0. So there should be upper or a lower limit should be 0 and remaining any one could be a plus or minus, it comes under any numerical value. And next one is bilateral value. In the bilateral value, both the upper and lower limit should have a same numerical value. Okay, and also it should have a same decimal values. So we have a diagram given to differentiate the unilateral and bilateral tolerance method. In A, unilateral tolerance has been given with basis of 20, which the upper limit has a 0 value with a minor lower limit has a minus 0.004. As for bilateral, basis of 20 plus or minus 0.002. Either you may write plus and minus symbol up and down and you may write 0.002 next to it, right? Or else you may mention plus 0.002 and next to that in downside minus 0.002. And another method is limit dimension. Both values should have the same number of decimal places, right? There should be not neither plus or minus symbol. There we can write directly write that 15.45 and the minimum value of 15.00, right? but the only condition is the decimal number value should be remaining same. Okay, formatting metric tolerance using basic dimension with the tolerance 45 plus or minus 0.15, right? So here this image shows the difference, which is on a wrong way to write and which is a wrong way which we want to avoid, right? The number of decimal places in the basic dimension does not have to match the number of decimal places in the tolerance, right? And for an angular tolerance, right? For an angular tolerance, it is same as an bilateral method, right? So for first one is a basic value, angle value of 30.0 degree with plus or minus 0.2 degree, right? Both the angle and the plus and minus value have the same number of the decimal places. So for angular, we want to mention a decimal value, basic decimal value, as well as the plus or minus upper and lower limit value. So thanks for all.